Alright, didn't get any questions emailed in advance. I'm going to give you fair warning. There's some issues on the YouTube side this morning. So basically, I had to log in twice to get this connection to work, and also it's kind of acting weird, like it's really low, really lagging to connect. So if we drop off, I do apologize now. I'll try to keep an eye on the channel as well as the studio itself that lets me see what's being recorded. But yeah, I'm getting some weird issues this morning. I'm hoping it's just kind of on YouTube side and it's clearing up. But did you get any questions? So if you got questions, please post them in the chat. I've got the chat window open. Looks like there's 3 of you watching right now. So again, post your questions. I'm going to kind of get some work done. But again, these are office hours. These aren't lessons or lectures. There's nothing pre-prepared here. So if you got questions, go ahead and ask them. All right, so just got a question. Can I go over functional versus substitutive ether functional versus substitutive ether naming? So I'm just bringing up the notes right now to make sure I'm not getting them flipped which one is which. I think I'm seeing the confusion. In the notes it says that you should name the ethers in alphabetical orders. And I've actually seen it done both ways. So in terms of the... Okay, so we've got 2 types. We've got substitutive and functional class. Substitutive is the more... versus functional class. So your substitutive here is more versatile. Your functional is easier. And typically what we see is the functional class naming. So the substitutive class naming is that we're going to treat this ether as a branch, and this is where our oxy name is going to come in. So the chain plus oxy. And just making sure I'm telling you this right. So for the ether, the shorter chain is going to get the oxy name. So if we have something like this is the ethoxy part, and this is the butane part. So 1-ethoxy-butane to indicate that we're attaching it to the one on the butane. Now, the reason why we want to go with something like the substituted naming class is for sheer merits that we have something incredibly complicated on our ether. So if we have like a whole bunch of branches, we have like stereochemistry, we would want to start working with this. And again, this epoxy shows up especially when you do benzene rings. So something we didn't really talk about that much are, let's say you had a structure like this. This would be 1,2-dimethoxy, or 1,3-diethoxy, 1,3-dimethoxy, 5-ethoxy benzene. So this oxy thing here, it just means that you've got an ether bridge. But again, this is going to only kind of be used if we've got something really complicated. In general, what we work with are the substituted class names, or the functional class name. In this case, we just name it group ether. Now the notes say by the length of the chain, but the thing is I don't see that. So if we look, I think it's actually by the length of the chain. So the shortest group first. I think that's just a typo in the notes. But everything I've seen, this is the shortest chain first. And that's the longer chain. Now with these, we don't want highly substituted compounds. So if you have something with stereochemistry on it, if you have something that it's not represented by a single name, you can't use the substituted class. But I do need to go look it up and check. I may have just been transcribing when I made the PowerPoints. I may have just made that mistake when I typed it out. But something like MTBEE, methyl tert butyl ether. This is why I'm pretty sure it's actually by the shortest, by the longest, not by alphabetical order. So MTBE is a very common ether. We used to use it for a lot of labs. We don't use it anymore. But MTBE is methyl tert butyl ether. Methyl ethyl ether is that. And if the two chains are the same length or the same group, this becomes the dies. So if we have two ethyl groups on opposite sides of an ether, this becomes diethyl ether. So functional class is actually the most commonly used, and the reason why it's most commonly used is that ethers are actually pretty benign compounds. We don't really do much with them. They are acid sensitive, so if you work underneath acidic conditions, you can decompose your ethers into their principal alcohols. So typically when it comes to running reactions, they're very good for basic conditions or neutral conditions, but if you try to run anything really acidic, you're going to degrade it. But they make great solvents. So lab we tried running for a while but never got up and running was a Grignard Lab, and that worked with ether because the ether wouldn't react with the Grignard. You can't do really substituted reactions on ethers with Grignard reagents. Drawback with ethers is that they tend to evaporate at a low boiling point. But again, the point here is that typically with ethers we have the functional class naming because we can conceive of situations where we are working with an ether with a lot of branches on it. Typically though, most common ethers are the simple ethers that are described by substituted class naming, which is what we use the most of because it deals with the most ethers we're likely to work with. Now you can also kind of see in the notes, it talks about special ethers like ethylene oxide, tetrahydrofuran, 1,4-dioxane, diglyme. The other thing we're going to start seeing with these ethers is they have a lot of trade names as well. So when it comes to these ether examples, we're typically sticking to very simple examples because that's what's mostly going to be covered or mostly seen. So yes, with functional class naming, you can come up with some very esoteric ethers to name. You're just not likely to ever run across them. And when it comes to more complicated ethers, we also typically find they have trade names more than anything else, so we don't really have an IUPAC rule to go with it. So again, I would say with ethers, don't overthink them. You're not going to get some like enormous nightmarish compound to name because you're not likely to ever run across them. Also, the ethers are kind of Chem 251 if you look at the SLOs. They're both in 252 as well, but they're not really the focus of this unit. Yes, I think it's actually by length of chain, and I remember that. So I think there's just a typo in the notes where it says by the alphabetical order. I think that was a typo from, it was carried over from when it was the functional class naming. So the functional class naming, you do go by the shortest ether. When it comes to substitutive, it's definitely, I'm sorry, when you name ethers with functional class, that's when you go back to the IUPAC rules of organizing them by, you go with the shortest chain, but you also organize where it goes in the name by alphabetical. So something like an ethoxy or propoxy, those are going to be treated like a branch on the parent chain, and so those get listed alphabetically. When it comes to the ethers, it's usually shortest then longest. Correct. So you're going to order them alphabetically, but again, your alkyl groups and your halide groups do have the priorities. So you're not going to minimize, you're not going to pick your first carbon based off that alkoxy group. You're going to pick it based off of your alkyl and halide groups. And so it may not necessarily be the lowest number. And this reflects the benign nature of the ether bridge. So if you've got a substituted ether, like a halogenated ether, the halogen is actually going to be doing the chemistry, not the ether, which is why that ether sits so far down on the priority list. Because pretty much everything outranks halide and alkyl groups. So alcohols, alkenes, alkynes, ketones, aldehydes, all of those have higher priority to alkyl groups and alkyl halide groups because they're more reactive. Carbon-oxygen-carbon bonds, those ether bridges, are so benign that even the alkyl halide is more likely to react first. All right, one from the study packet, which I'm probably going to need to download. In terms of one that actually is easy to name. Page 4, last example. Oops, not ring. So your substitute class, this is your ethyl cyclopentyl ether. And by your substituted class, this is going to be ethoxy cyclohexane. Now, we're not going to find good examples where you can use both, because typically if you're dropping into this functional group naming, it's because this is an overly complicated compound which can't be named by this. But I would say this is ethyl cyclopentyl ether, and this is ethoxy cyclohexane. And yeah, even on the even on page 5, the ethyl butyl ether, that's named by increasing carbon chain length. Cyclohexoxycyclohexane. Man, that's just when you really hate yourself. Yeah, generally we're not going to find one where we can do both easily. Yeah, you're welcome. So you've got two classes in naming that were created for two different reasons. So particularly with organic too, this was when I was told in college that the IUPAC naming breaks down a lot. And Kay Sandberg was right. It does break down a lot. I don't see a reason why you would be. So if you look at something like diglime, so diglime's got the 3 ether oxygens in it. There is probably an IUPAC name for that, but no one uses it. They call it diglime. And so, particularly with the organic 2 material, I think part of the reason it gets easier is that we become less reliant on IUPAC just for sheer merit of practicality. There are rules in IUPAC for how to name these things, but you start coming up with so many different permutations and computations of how you can be putting these molecules together with their different functional groups that ultimately you can't really name it, or there's no way to conceive of a system where you could uniquely name things. So IUPAC is a very good idea, but the practice of figuring out like thousands of rules that anyone could practically memorize, in fact, if you look at the IUPAC rules of Wikipedia, it's like a 20-page stuff. It just becomes impractical at some point. So the nice thing about organic too is that we actually start seeing simpler and simpler molecules because the rules for alkanes are really straightforward. So we can give you these really complicated alkanes and you should still be able to name them. But let's say I throw something in there that has an ether, an aldehyde, a ketone, a carboxylic acid, and a benzene ring. Well, there are a lot of rules that you would have to know off the top of your head, and there's just no good way to approach those types of problems. And so we end up having to come up with these very simple examples because they're the only ones that don't require you to memorize a 20-page list of rules. So you do need to know the naming. Like, this is not to disparage IUPAC naming, but to understand that you're kind of seeing the fact that you can take what looks like a very simple molecule and end up creating a very complicated problem unintentionally. And so the tendency here is to stay towards simple examples because the simple examples are the ones that aren't unwieldy. But as far as like creating multiple alkoxy groups on the chain, like you could, but that's just an exercise in like functional group naming or functional class naming. So you'd have like you'd have ethoxy, propoxy, whatever the names of the groups are, and you would just name it as normal. But on top of that, like other than examples like that, what else do you really ask? Because if we start throwing like aldehydes and ketones on there, this becomes such complicated molecules. They just become nightmares to look at. We kind of saw this when we looked at kinetic versus thermodynamic product, is that you can quickly open up you can take what looks like a very simple molecule and turn this into a really complicated problem. Where if you have asymmetry in the molecule, suddenly you have to consider which way you number the carbons, you have to consider like resonance stabilities and things like that. So I would say we're going to stick to simple examples by pure merit of practicality. Yes, I can come up with some enormous nightmare molecule, but like it may be impossible to name it, or you may see contradictions in the IUPAC naming because IUPAC simply can't conceive of all the different combinations you could come up with. This is something I noticed with the Heck reaction and the Michael reaction. So for the next unit, it was very easy to take a couple molecules and say, okay, run the Heck reaction. But then you begin to realize, like, okay, so the Michael reaction is a better example. So we run the Michael reaction, and with the Michael reaction, okay, you get carbon-carbon bonding, but there's things that can happen after the Michael reaction occurs. So you have Robinson annulation, you have decarboxylation, but it's a very simple reaction to start with, but there's so many different directions it can go after the initial reaction runs. So unfortunately for the Michael reaction, we're going to have to stick to really simple examples, so it feels like we're just kind of doing the same reaction over again with just like a couple of groups changed. But the reason we're having to do that is that, okay, if you throw a carboxylic acid on it, suddenly it can go do decarboxylation. Or if we have an aldehyde or ketone on it, suddenly we can get annulation, and the right answer ends up being super complicated just by changing one functional group. So yeah, hopefully this is kind of assuaging your concerns, is that yes, there is potential to make these problems very complicated. That is not the design of this course. I mean, as an instructor, I have to come up with the answer too, right? Like, I have to figure out what that answer is. And so for like the exam that you took, there was one problem where most people didn't do the Diels-Alder reaction, which was the intent, and I take out points for that. But you just missing that there's a Diels-Alder component in there, now you've got a wrong answer. But how are you, like, what if you don't see it? Like, what if you don't catch that little thing? Right, I'm going to put up the intermission sign up again. So next question about cis versus trans alcohol. So it depends. So if you're working with things that can rotate, so you're working with linear alkanes, they have to be trans for the reaction to occur, but if in the drawing they're cis, you can just rotate them so they're trans. The complication here is that because you're doing that rotation, you need to check at your final products to see that they're correctly oriented. So I think example in the notes, you're given R1, R2, OH, R3, R4, and let's say we have bromine here. Now, as written, these are cis, so they can't undergo a epoxide reaction. So if you add hydroxide to this, nothing's going to happen. So what will happen is it'll rotate along this bond, and you have the OH up, R1 and R2 are still down, but now R3 is back and up, and R4 is now forward. So wedge, dash. So now R4 is out, and it can undergo a reaction, and so we change the position of R3 and R4 relative to each other because we have to rotate to get to the transposition. But if we have a cyclohexane ring, the reaction doesn't happen. So if we have conformational, if it's fixed because of conformations, meaning that we're in a ring and there's no way to get rotation along that bond, if your alcohols or your alcohol-alkyl halide are cis to each other, no reaction occurs. The hydroxide is going to do what hydroxide would do otherwise, which probably would be substitution of the bromine to give you a diol, but still not going to do you any good. You're not going to form the epoxide. If they are trans, then you will get a reaction. But the cyclic rings are the only situation where they absolutely have to be trans to each other for the reaction to occur. For the linear alkanes, it can happen whether they're cis or trans is drawn because we have that bond rotation. But if we do have that bond rotation, you need to keep in mind where things are, because you're actually going to have to rotate the molecule, which will change what your final product looks like relative to your starting drawing. So I got a question to an example of forming an epoxide from a ring. So let's say we have cis versus trans 1,2 cyclohexadiol. And we add hydroxide to this. For this one, there's no reaction. So this consists a solution of hydroxide, and at worst we might get elimination, but probably nothing's going to happen with this one. With this one, we're going to deprotonate one of the alcohol groups. It's going to attack the carbon, pop off the hydroxide, and what we'll finish up with is this epoxide. Now I don't really need to draw the stereochemistry in there because it's got the mirror plane, so it's a meso complex. Is this a good for Orgo 2? Actually, it's open to anyone. So if you do Orgo 1, if you do Chem 1, Chem 2, you can ask any questions. So this is kind of just office hours. If you were to show my office hours, I would answer any questions. But for rings, the leaving groups have to be trans. So let's say we had darker pen. I can only hope. Nope. Nope, there you are. So let's say you had this ring. So you have the 2,6 dibromocyclohexanol, and you hit it with hydroxide. So we're going to go through this alkoxide intermediate, and it has a choice of which one to attack. And attack the bromine that's cis, or the one that's trans. This one is the wrong orientation. So this alcohol here is going to attack the trans bromide, and we're going to end up getting this epoxide when we're finished. So if you have an alkoxide and it has two groups that it can attack, and you're curious if it forms an epoxide, which one will form the epoxide with, it'll form the one that's trans to it for the epoxide. So in this case, we would never form the one where this bromine on the right is left behind. So let's actually swap this out with chlorine. We never form a complex where it was the chloroepoxide. We'd always have the complex where it was the rhum epoxide, because the bromine there isn't in a position to be pushed out. The chlorine is. Mostly substitute comes the rings, or is that only for linear ones? It's still going to apply for rings. Well, okay, so the complication with, so yes, it's going to still apply like it does for rings as well. So that carbocation intermediate, if you have two alcohols, or if you have two groups, because the question is, I know what the question is, I'm trying to think of how to articulate it. So you change the mechanism if you go from acidic to basic conditions. So for acidic conditions, you go through a carbocation intermediate. For basic conditions, you don't. So this is the difference between going through like an SN2 pathway versus an SN1 pathway, which is effectively what you're doing with an epoxide. The alcohol is substituting the local groups. It's still going to apply in the same way. So the mechanism will change. So let's say you had a methyl chloro versus a non-chlorinated version, and well, we're going to do alcohols down here, aren't we? OH versus OH. If you do this under acidic conditions, so the H+, you're going to go through a carbocation intermediate, which means that this one is going to pop off and you're going to form the epoxide here. And then if you go under basic conditions, I know it's not as easy for rings. I know that much. Hold on. Let me bring up the notes really quick to make sure I'm telling you the mechanism correctly. And then I'll get to the next question I got asked. Short answer though is yes. It's going to, okay, so it's the ring opening that you're asking about. So in terms of ring opening, yes, it's going to follow the same approach. If we're opening up a ring like this, and we do acidic versus basic, because of the carbocation intermediate with this one, we're going to end up putting the alcohol on the least substituted carbon through a carbocation intermediate. For base conditions, we're going to end up putting the alcohol on the more substituted carbon. But yes, the same rules still apply for rings that they do for linear alkanes. For hybridization, I know if there is an empty orbital, then it has less bond numbers and therefore less hybridization. Keep an example on that, a p orbital. So an example of this would be something like boron, as well as carbocations. So a molecule like boron, or an atom like boron, is sp2 hybridized, with the boron itself having a vacant p orbital, no charge on it. So this is why boron is a very good Lewis base. Your carbocations are also an example of this. So if we have C, CH3, CH3, CH3. The carbocation here, that's a vacant p orbital, and the hybridization here is sp2 hybridized. If we had lone pairs in it, then this would give us our sp3 hybridized carbons. You're welcome, Dia. How do you know if it has an empty p orbital? So you have to kind of look at the starting molecule. So we're going to kind of cheat and we're going to use trends. Typically, if it's got 3 bonds and no lone pairs on it, that's when you're going to have the empty p orbital. So that's kind of how I remember it. So right now I'm just trying to go through like how I would check. So for me, if I see 3 bonds and I don't see, especially if it's trigonal planar, then, and it doesn't have any lone pairs on it, then it's going to have that empty p orbital. So a carbocation has an empty p orbital, boron has 3 bonds around it, no p orbital. But something like, if you see those lone pairs on it, that's not an empty p orbital, that's a p orbital containing electrons. Correct. So if you do end up creating chiral centers, you do need to note which one you get. Sometimes you do get limitations. So particularly if you're not going through that carbocation intermediate. So the carbocation intermediate will give you both R and S configurations on the second carbon. You typically have more of an SN2 pathway under basic conditions. So for the SN2 pathway, you're going to uniquely get one product. So Basically, undoing epoxide reactions is just an SN or SN2, SN1 or an SN2 pathway. And the same rules are going to apply. So if we're under acidic conditions, this is basically an SN1 pathway. Well, what we're substituting off is this bridging oxygen. If we're under basic conditions, it's going to fall in an SN2 pathway. And we're still going to get that same rule. So for this, we're going to get a mixture of the two chiral centers here. For this one, we should only get one. And this will end up being, let's say we're substituting with X. So our OH goes up. Another group goes down. X is going to be down. And so in this case, we're going to end up with uniquely trans OHX. In this, we're going to end up with a mixture. So our OH is up. And then whenever X is coming in, we're going to get a mixture of the RNS forms of that. Yes. Now again, we're going to kind of stick away from like super complicated examples. So something simple like this, you're going to end up getting, particularly if you go through the base pathway, you're only going to end up getting one. With this, you're going to end up getting at most two, but you can definitely conceive of far more complicated examples. Wow, I was lazy in the end of the textbook. So for 3, it's definitely not. Boy, I sure do love textbooks. So with carbon, if carbon has 4 bonds, it doesn't have a vacant p orbital. So for carbon having its p orbitals occupied or unoccupied, we have to specify it. So the example here. That pins on his last leg. Do love it when a textbook does not draw in everything. So you want to look at 5 and 6. So this carbon has 4 bonds. It's got a hydrogen, carbon, a double CH2. 4 bonds means there's no p orbitals. Because carbon does 4 bonds, the only way to have a vacant p orbital is to have it missing a bond. 4 is the same way. Carbon here, 2 bonds off to the side, 1 hydrogen, because we have the 4 bonds. This doesn't have a vacant p orbital. The only way we can get a vacant p orbital in carbon is through a carbocation. So if you don't see a carbocation, carbon doesn't have a vacant p orbital. For naming diols, diols don't have to be on adjacent carbons. A lot of the examples we work with in this class, they are adjacent because we're trying to form epoxides. But you can have diols, triols, tetrals, things like that. So 1, 2, 3, 4, 5, 6, 7. So this is 2, 3, 4, 6, heptane, trial. There is no reason that they have to be adjacent. That just happens to be a lot of the examples because we are focusing on epoxides. But you can have more than two, you can have them all over the place. And basically the big difference between alcohols and polyalcohols, is that now you have to start specifying multiple alcohols and specifying in the name that you've got more than one. I'm going to ask, do you ever the 4 steps of Sn1? I'm not familiar with there being 4 steps to Sn1. So for Sn1, this is a nucleophilic substitution. And with the Sn1, typically we have our leaving group, so we'll just represent it with an X. And first step is we break the carbon X bond, just as generally to form, can form an anion, depends on what our leaving group is. And this will give us our carbocation. This ends up being a very good Lewis base. And so whatever our nucleophile is next, our nucleophile will attack, in a separate step, it'll attack the carbocation, and it can attack from top and bottom, so we'll end up getting either the nucleophile added to the bottom or the nucleophile added to the top. And this does have implications. This means that if we end up with chiral centers, so if we have R and S chirality, we're going to get a mixture of both, usually racemic, so 50-50 mixture of both the R and S conformation, depending on where that nucleophile attacks. So that's your Sn1 pathway. First, you break the carbon X bond, or your leaving group. Second step, your nucleophile attacks from both top and bottom, and this will be your 2 steps. I'm not familiar with there being 4 steps for Sn1. Now, if you have an alcohol, there's more steps, but they mostly come about from turning this into a leaving group. So with the alcohol, you can get protonation. So step 1 is protonation, 2 is leaving, 3 is substitution. You're welcome. All right, that's kind of the end of the office hours today. So again, if you ever have questions, please feel free to email them in advance or ask them in the comments. And I will see some of y'all tomorrow.